The topic of my presentation is development of high-performance electrochemical capacitors for supercapacitive swing adsorption of carbon dioxide. I'll start with the big picture and the motivation behind this research topic, and then I will introduce some of the recent work that I have done and some of the work that I'm going to do in future. Just to give you some idea, 19 of the hottest years on record occurred in the last 20 years. The picture here shows the overview of Earth captured by NASA in the year 1974 to 1978 when the concentration of CO2 was around 320 parts per million, and in the year 2017 to 2021 where there is a 100 parts per million increase in CO2 concentration. And this scale shows a clear rise in temperature. The rising temperature was directly related with increasing levels of carbon dioxide in the atmosphere. Especially after the year 1970, there was an exponential increase in CO2 concentrations, which has caused the global temperature to rise by 1.2 degrees Celsius within the last 4 to 5 decades. Currently, the global emissions of CO2 is around 40 billion tons per year, which is a huge number. And according to the Intergovernmental Panel of Climate Change (IPCC), we would need to reduce this number down to 20 billion tons per year if we want to limit warming to 1.5 degrees Celsius. Currently, there are many technologies that are being developed to capture CO2 from various sources. Capturing CO2 from multiple sources have two basic types. One is capturing CO2 from centralized sources, which contain CO2 in the range of 4 to 20%. These sources include emissions from power plants, cement industries, coal producing power plants, and they contribute around 60% towards total emissions. The minimum thermodynamic work needed to separate CO2 from a mixture of gases is around 7 kilojoules per mole of CO2 in this case. Decentralized sources have CO2 concentration ranging from 0.04% to 0.4%, and they contribute around 42% towards total emissions. The minimum work needed to separate a CO2 from a gas stream of 400 ppm is around 22 kilojoules per mole. Currently, there are many technologies which are used to capture CO2, but before that, I will discuss some of the technological requirements. So, for a CO2 capture technology to be highly efficient, it should have high absorption capacity, it should be highly selective and consume very low energy. It should have fast absorption kinetics, and the materials that it uses should be non toxic, stable, cost effective, and should have a longer cycle life. Current technologies include temperature swing adsorption and pressure swing adsorption on porous solvents such as zeolites and other covalent organic frameworks or metal organic frameworks. But the problem with temperature swing or pressure swing is their high energy consumption, and they can also cause moisture. They also have moisture sensitivity. Relatively new technologies include electrochemical swing, in which we increase or reverse the potential to capture and release CO2. And in moisture swing, an anion exchange resin is used. When the anion exchange resin is in wet condition, CO2 gets adsorbed, and when it is in dry conditions, CO2 get adsorbed, and when it is in wet conditions, CO2 gets desorbed. Some of the technologies are mentioned in the picture on the right, where we have physis option, alkalines option using sodium hydroxide or potassium hydroxide solutions, amine modified materials, amino acid solutions, moisture swing, and electrochemical swing. As I discussed, most of these technologies use temperature or pressure swing, which have high energy requirements and they are sensitive to moisture. So electrochemical swing is rather have more advantages in the sense it does not require any temperature or pressure swing. It just uses an electric potential, and the material that it uses are more environmental friendly. So in the following slide, I will discuss some of the recent technologies on electrochemical swing adsorption. Electrochemical carbon capture include using electric potential to capture and release CO2. There are basically two different types of electrochemical CO2 capture. One is pH swing, and the other one is using redox active carriers. The use of redox active carriers is again not so feasible in the sense that it uses expensive materials such as carbon nanotubes, ionic liquids, and also the uh, electrolyte or other solvents that it uses. For example, quinones, they are oxygen sensitive. On the other hand, pH swing adsorption, what happens is as we apply electric potential to the cell, a pH gradient is created inside an electrochemical cell, and due to pH gradient, when the pH goes up, means it goes higher to a higher value. CO2 gets converted to bicarbonate or carbonate ion depending on the pH, and when we reverse the potential, bicarbonate or carbonate ions go back to carbon dioxide gas. In this way, we can capture and release CO2. Currently used pH swing technologies include electrolysis, bipolar membrane electrodialysis, membrane capacitive deionization, and supercapacitive swing adsorption. Electrolysis and bipolar membrane electrodialysis, both of these techniques use ion exchange membranes, and they have very high energy consumption, which makes these technologies cost prohibitive. Membrane capacitive deionization is a recently developed technology, and it has very low energy consumption, which makes it advantageous over other electrochemical technologies. But it still requires the use of ion exchange membranes, and it also has low absorption capacity and low absorption rate. Supercapacitive swing adsorption uses electrical charges stored in the supercapacitors to capture and release CO2. This technology is energy efficient. It is capable to work below 100 kilojoules per mole of energy. It does not require the use of ion exchange membrane, which is a great advantage as compared to other electrochemical technologies. The disadvantage that it has is low absorption capacity and low adsorption rate. In the following slide, I will narrow down my talk to supercapacitive swing adsorption because this is one of the topic which I am working on, and I will explain some of the working mechanism behind it and some of the recent research that is being carried out in this field. So, as the name suggests, supercapacitive swing adsorption uses supercapacitors to capture carbon dioxide. Charging and discharging of supercapacitor electrodes results in capture and release of CO2. Uh, this picture basically shows two porous electrodes connected with a power supply. As we switch on the voltage, one of the electrode gets positively charged and the other one gets negatively charged. The ions from the solution, for example, cations will move towards the negatively charged electrode, and anions will move towards positively charged electrode. In the solution, we also have H plus ions and HCO3 minus ions, and because of the attraction of electrodes towards these ions, protons will move towards the cathode, and this movement of protons towards cathode can create a pH gradient in the bulk solution. This pH gradient or increase in pH can drive the CO2 equilibrium towards bicarbonate or carbonate, and in this way, we can capture carbon dioxide. Similarly, when we reverse the potential or discharge the supercapacitor, we can release carbon dioxide by shifting the pH back towards lower values by increasing the proton concentration. The figure on the right shows a graph between voltage and CO2 concentration change against time. The black curve show the changes in voltages, and the blue curves show the change in CO2 concentration. As the voltage is increased from 0 volts to minus 1 volts, we can see there is a rapid decrease in CO2 concentration. Then, as we keep the voltage at minus 1 volts, CO2 concentration reaches back to equilibrium and it achieves its full adsorption capacity. Similarly, as we discharge the supercapacitor, CO2 adsorption, CO2 gets desorbed from the electrode surface, and then during the holding step at 0 volts, it again reaches back to equilibrium. In this way, we can charge and discharge our supercapacitor to reversibly capture and release CO2. Other possible mechanisms include the adsorption of carbon dioxide to the electric double layer and the physisorption of carbon dioxide to the hydrophobic pores. The first report on supercapacitive swing adsorption was just